quarter for group 1, and we did the Copernic experiment. So the overview of this experiment is that it demonstrates how material property can be determined through measurements of both saturation pressure and temperature. The objective of this experiment is to determine latent heat of vaporization of water using the Copernic equation over a range of temperatures and pressures, and then we're going to verify them using the steam tables. So the apparatus that we used was, we had a flask that had glass beads in it with a rubber stopper that was heated by a hot plate with a thermocouple, and a transducer with a mechanical pressure gauge. And we had the air bleed valve and the vacuum control valve both closed during the experiment, and we had a centrifugal pump pumping up the water from the water reservoir, and we had a computer system to collect all the data. So the theory behind this is that the whole objective was to find the latent heat of vaporization, which is HFG, and it can be calculated in two methods. One is what we did in the lab. We experimentally got measurements of pressure and temperature values using the Copernic equation, which is the derivative of saturation pressure over saturation temperature, which is equal to SFG over the specific volume, which is equal to latent heat of vaporization over the specific volume. So the first thing that we were tasked with was to simply just graph our results and also graph the tabulated values from the steam tables, which, as you can see, they have similar slopes, but they're not exactly the same. And then for the procedure 1, we wanted to calculate the latent heat using the ideal gas law. So we don't exactly know what the specific volume was, so we used the ideal gas law, which is pressure times specific volume equals the ideal gas constant times temperature, and if we rearrange that, we can get the specific volume equals the saturation temperature over temperature times ideal gas, and then we can rewrite the equation as the derivative of pressure saturation over temperature saturation equals the latent heat times pressure saturation over saturation temperature squared times the ideal gas constant. And then, well, we want to find latent heat, so we rearrange it and get that equation. And then we graph it, and the issue with this method is that there's a large degree of error due to the derivative that we're deriving. So they don't match up. We want them to have pretty much the same slope. So this one's very much not accurate. And for procedure 2, we took a trend line over the pressure versus temperature, and we got a function that we use to create the pressure saturation equation, which is equal to 0.158 times the exponential of 0.0468 t, and then also define the derivative, which is equal to 0.00739 exponential 0.0468 t. And we're using the same equation to plug it in to create a graph, which, as you can see here, I know that theoretically this graph is not right. It should be more, they shouldn't just slightly intersect, they should be pretty on top of each other. So I'm pretty sure I used the wrong trend line to find that value. And then for procedure 3, we're doing the same thing as procedure 2, except this time the latent heat is equal to A plus B of t. And then once we interpolate the data, we have to find both C1, C2, and C3, which was done using the regression software in Excel. And then you get your C1 value, your C2 value, which gives you your A value that you can plug into your HFG equation, and also your C2 value, which gives you your B value, which you can once again plug into your latent heat equation to create a graph that is linear. And in conclusion, procedure 1 was the most inaccurate method due to large errors associated with derivatives. Procedure 2 is more accurate than procedure 1, however, this is dependent on the equation derived for the desired temperature range. And out of all of the procedures, procedure number 3 is the most accurate and is able to predict P of T and the derivative of P of T as a function of T over the whole temperature range. And in discussion, we had beads in the beaker because from heat transfer we know that for heat, it is heat flux times the surface area, which if you have more surface area that's created by the beads, it would heat up your process quicker. And a modification that I would make to this laboratory is using corks. Instead of using corks to seal off the tops of the flasks, I would use a screw on top, because an issue that we ran into was that the corks were like popping up off of the gauge in the very beginning, and we'd have to like seat them back down. Those are my references. Any questions?